Welcome back to The Explainer. Look, today we're cutting straight through the industry hype to master NVIDIA Cosmos physics. If you've ever watched your robot absolutely nail a complex task on your monitor only to instantly drop the ball, literally, or just completely fail to navigate in the actual physical lab, yeah, you already know the painful, persistent problem of sim-to-real transfer. So our goal today? We're looking at the hard data, structuring our deployment strategies, and finally solving that reality gap once and for all.
It's the core paradox keeping technical leads up at night, right? You spend 35 grueling hours meticulously tuning a simulation. You get the lighting, the friction, the physics looking absolutely perfect in your digital twin. You finally push that validated policy to a physical robot, and you watch it immediately fail. It is incredibly frustrating, and frankly, it leaves us all scratching our heads asking, why is this still happening when our sim tools are supposedly better than ever?
Well, the answer matters, because getting this wrong isn't just about lost engineering hours. It's hard, bleeding cash. We're talking about a $4,500 to $7,500 monthly financial drain per project, directly caused by these failed transfer attempts and wasted robot operation time. Multiply that by a team of 10, you're looking at a catastrophic budget leak. The stakes for getting your simulation deployment strategy right are sky high right now. We literally cannot afford a trial and error approach anymore.
Okay, Section 1, the sim-to-real reality gap. Let's map out exactly where the robotics industry stands with simulation tech today.
Tracing our rapid evolution, it's wild to see how aggressively this technology is moving. Just a couple of years ago, back in 2022, we were entirely reliant on traditional, rigid physics engines. Sure, they were fast, but fundamentally limited in handling complex, real-world physics. Then, 2023 hits, and Isaac Sim gives us our first real taste of hybrid neural approximations. Fast forward through the Cosmos preview, and now with the Cosmos 1.0 launch, we have a neural physics engine achieving incredibly high fidelity. This shift toward predictive world models, it's a massive paradigm shift. It is fundamentally changing how robots learn about physical spaces.
But wait, the crucial takeaway here is that 15% number. That is the residual reality gap with Cosmos 1.0. We really need to bust the myth that Cosmos is some magic bullet that completely eliminates real-world training. Because out of the box, it absolutely does not. Now, don't get me wrong, the gap has shrunk massively from the 30 to 40% failure rates we saw just a few years ago. But that remaining 15%, that is exactly where deployments succeed or completely crash and burn in production.
Jennifer Martinez over at Boston Dynamics frames the reality of this perfectly. Achieving a 73% reduction in real-world training is a massive, game-changing cost savings for any robotics team. But you absolutely cannot ignore the second half of her statement. Bridging that final 15% still required 200 hours of domain randomization tuning. You know, domain randomization, intentionally introducing digital chaos into the sim, changing lighting, friction, object weights at random, just so the robot learns to handle real-world unpredictability. You have to budget the time and engineering power for this tuning phase. It's non-negotiable.
Which brings us to Section 2, Cosmos versus Isaac Sim. Let's dig into the critical pain point of platform selection, so you don't blow your entire budget on the wrong software.
There is a really stark contrast in the required resources you need to be aware of before deploying. If your robot is entirely rigid, think of your standard industrial robotic arm, Isaac Sim is vastly faster at 500 frames per second, and much cheaper to run, only needing 12 gigs of VRAM. But if you're working with soft grippers, cables, or any deformable objects, Cosmos is completely mandatory. So you're making a definitive trade-off here. You drop your frame rate and double your memory requirement to 24 gigabytes to get that advanced neural physics accuracy. Basically, you have to choose your engine based on your robot's physical makeup, not just the marketing hype. Moving on to Section 3, Surviving World Model Training. We need to talk about the anxiety-inducing reality of world model convergence.
It is incredibly easy to see why a staggering 73% of training runs are aborted by panicked engineers. Look at this. During the first 48 hours, the loss curve, which measures how poorly the model is performing, is violently fluctuating up and down by like 50%. It genuinely looks like the model is completely failing. If you're staring at the dashboard at 3 a.m., your natural instinct is to kill the run and check your code. Don't. You must survive this chaotic window. Because if you hold on, somewhere between hours 48 and 60, you hit a sudden phase transition. The model suddenly gets the underlying physics representations, and it will eventually converge to 95% fidelity by hour 96.
MIT's Alex Thompson validates exactly what we're talking about here. Engineering patience is literally the key skill for a successful training convergence. The model isn't failing early on, it's transitioning from just memorizing the training data to actually understanding the physics. If you panic and stop the run at day 2 because the charts look messy, well, you haven't saved time. You've just burned massive amounts of expensive compute to generate a completely useless overfit model.
Let's jump to Section 4, Hardware Requirements and Costs. We really need to look at how you should be optimizing your GPU spend.
The cost optimization reality here might actually surprise you, because currently 68% of teams are drastically overspending on GPUs due to confusing documentation. Buying a single massive 6000 ADA graphics card for $6,800, that's actually a mistake for most teams. In simulation training, you need enough memory to handle a large batch size, meaning you're running multiple parallel robot simulations at the exact same time to learn faster. A dual RTX 4090 setup gives you the required 48 gigabytes of total VRAM across 2 cards. It handles the necessary batch sizes effortlessly, and get this, it processes at nearly double the frame rate, 160 FPS, for less than half the price of the ADA. It's a no-brainer.
All right, now that our hardware is optimized, Section 5, Closing the Reality Gap. Let's focus on actual, actionable solutions to bridge that stubborn remaining divide.
Remember how Boston Dynamics spent 200 hours tuning? Well, here is a highly streamlined 20-hour auto-tuning pipeline to get you there way faster. First, systematically measure your real-world sensor variance. Then, set your randomization to the mean plus or minus 3 standard deviations. Why 3? Because mathematically, that covers 99.7% of all the wild, real-world edge cases your robot is ever going to encounter. You test, you validate, and you iterate. This strict protocol eliminates the total guesswork that causes 73% of teams to under-randomize their environments and ultimately fail when they deploy to the physical world.
And this is exactly why you cannot rely on a single physics engine. You absolutely need a hybrid strategy. Look at this. Cosmos is incredibly accurate for soft contacts, hitting 95% success. But its neural engine struggles massively with rare, rigid contact events, suffering a severe 30% performance drop. So, best practice dictates implementing a smart classifier in your code. Have it actively switch back to the traditional Isaac Sim solvers for those specific, highly precise rigid assembly tasks. That ensures your system maintains maximum robustness across literally every scenario.
Finally, we need to look ahead to Section 6, the 2027 Cosmos Roadmap. Let's talk about future-proofing your entire simulation pipeline.
Over the next year, migration pain is going to hit engineering teams incredibly hard. World model architectures are evolving so fast that major structural changes are rolling out every 9 months. And yeah, that frequently breaks backward compatibility. You are looking at losing 40 to 60 engineering hours per major upgrade just to fix broken APIs and retrain checkpoints. The core takeaway here is absolutely vital. You must pin your Cosmos software version strictly and build adapter functions to isolate your code until the long-term support version finally launches in 2027.
I want to leave you with this provocative question to take back to your teams. Are your APIs abstracted enough to survive a total architecture shift every 9 months? Because if your entire pipeline is hard-coded to today's Cosmos version, that technical debt is going to absolutely crush you. If you aren't prepared, the time to restructure your pipeline isn't next year, it's today. Thank you so much for joining me on The Explainer. Stay focused, keep iterating, and I'll catch you next time.